a little bit of awkward silence in the beginning. That was good. So, it is on. It says on. It's on. Good. So, welcome. We still have seats in the front. And by the way, you can win stuff at the end of the day. So, it will be an interactive talk. So, we'll ask questions. Feel free to participate. On the right side, if you want to skip ahead in the presentation, you shouldn't. But if you want to take it home, this is the barcode for it. And then later on, we will have some more links, stuff like that. And of course, the presentation will be shared. So that's me. And because we don't have enough time today, I'll make it quick. The most interesting part about me is that I started Java with version 1.0. Anyone here started Java on version 1.0? I'm not the oldest. Oh, that's great. I was in Poland at DevOps, and nobody raised their hand, so it was kind of odd. I'm normally more a QA person, but by accident we got into performance in Java, so I'm also a performance tester. You find me on all these social networks. I'm not very active, but of course I retired my whatever account. Good. So someone paid for this. This is the company Acceptance I'm working for, I founded with. We have a performance test tool which reads a lot of data, hence my interest in the 1 billion row challenge. And let's get to one of the things I find very important. I haven't seen on all the other slides. Everything you find is open to reuse, to be reused. Just quote me that you got it from me. You can change it, you can copy it, whatever you like. All the source code is Apache licensed. So this part is important for me. Though, of course, if you want to rate me, you see the icon there. So, did any one of you participate in the 1 billion row challenge? Who knows what the 1 billion row challenge is? A few hands. Okay, good. So, in January of 2000, well, in the end of December 2023, that guy, Gunnar from Hamburg, got bored during the holidays, as Germans typically do. His wife complained and said, you know, you are annoying, do something. And he said, okay, let me do something. And he came up with a community challenge for whatever reason. He can explain this way better. And he said, okay, let's ask the community, how can we read a file of data? I will show you the format in a second. And to make this challenging, let's have 1 billion rows. So his challenge was basically this input format of cities and temperatures, kind of readings you take over a period of a month, for instance. And this was the expected outcome, which is a tree map to a string, because Gunnar was lazy to use JSON or any other thing, so just basically tree map to string. He said, okay, we have 1 billion rows, and the size of the file will be about 13 to 14 gigabytes. So he set up an initial baseline. We will see this in a second. And he basically asked the community, hey, how fast can this be? And he basically restricted things a little bit, and also I participated in the setup of the challenge as well. People got nuts quickly. So everyone wanted to use Rust and C and other things. He said, no. It's Java only. If you want to do your Rust project, do it differently, do a different branch. Don't come with Rust code. I can't compile it, stuff like that. So it's Java only. Any GDK you can grab legally using SDKman, you can use. Every command line parameter you can find that's valid with this GDK, that's yours. No external dependencies, so the Maven compile was kind of quick. We will measure on bare metal, so at the end of the day we used a Hetzner machine. And Hetzner is a German cloud hoster with bare metal machines, relatively cheap, but really, really cool. And we just rented their 64 cores and 128 gigabytes of memory, but the challenge was restricted to 8 cores. Just to avoid that people haggle over caching, we said RAM disk only, file cache, so everything is in RAM, you are not really going to disk. You couldn't pre-process anything, so no cheating. 5 measurements, the middle 3 were averaged, and this is the important part in this challenge, startup and shutdown of the VM were part of the measurement. So that's one of the reasons why at the end of the day the Graal VM was winning, because startup and shutdown was part of the measurement. We had initially 400 cities in the mix. We had a kind of a stretch goal with 10K, because suddenly we realized, or Gunnar realized, I was just doing the hardware stuff, Gunnar realized that people started to cheat on the hash codes, for instance, of the cities. So let's give a second data set for validation, and suddenly a lot of these solutions died because they couldn't handle things efficiently anymore. You got only valid UTF-8 data. Nothing was wrong with the file, always nicely line-ended, always standardized line endings, Unix only, and temperatures were kind of nicely formatted, always that format, always 1 decimal digit, stuff like that. So everything was kind of a little fixed. And here's the question, and if you know, please hold back. So what do you think, how long does it take if you have a naive baseline implementation, let's say streams, to read this huge file, process all the information, and come up with the output? Anyone? 1 minute? You can win something. This is not a Christmas free thingy. It's not. If you go to a festival, you will find a poncho, a rain poncho in it, just in case you need one. So, 1 minute. Anything else? Anyone else? Wow. 2 minutes? 3 minutes? 4 minutes? 20 minutes. Okay. It's kind of 6 minutes. So, that's yours. You're welcome. And by the way, if you change the hardware, it's 150. The difference is, when I started this last year to give this presentation, I had only the DigitalOcean Intel machine available. And then later on, I switched to the Hetzner cloud machine, and suddenly I realized all the measurements were totally off. Why? So I rerun everything, and now you will see always basically 2 things. If you go with the left cloud, if you go with the right cloud, different measurements. This will be part of the story at the end of the day too. So we were kind of permitted to use 8 cores. So the multi-threading solution in streams is slightly disappointing because it doesn't really scale. It doesn't really use the 8 cores. Even if you have different hardware, it's just twice the speed, which is not cool. So what is the winning solution? What's the runtime of the fastest? By Thomas Würtinger, who is the lead engineer of the GDK Graal team in Zurich. So he knows how to do things. 8 seconds? 1 second? 4 seconds. Okay, let's do the single thread version first. 4 seconds? 1.5. So the single core one is 9 seconds on this hardware. On the other hardware, it's slightly less. And the winning solution is 1.2 seconds. So if you and everyone else, please just, I'm good, is 1.2, 1.6 on the AMD one, you can see that things don't play out as you would expect. The AMD one is not always the fastest one. And what we want to do today, because first of all, we don't have that much time, and if you look into the original solution, you won't get it. It's just a lot of code that works. It's a one-time solution. You can't maintain it. You can't really take anything away from it. It's, let's call it awesome code, but it's not for reuse, not for everyday use. So we will do the lame one today, 20% as the goal, which is 50 seconds here, and which is 30 seconds there. Okay, good. So I wrote this, you see the GitHub there. I wrote a small framework just to do all the testing. We don't measure the startup in our solution and the shutdown, so we don't have to do any Graal stuff. And we modify the results slightly because we also want to put the count of the cities in the result, not just the temperatures, but also how often we have seen the city. At the end of the day, this kind of becomes important. Okay, so the 50 minutes I have, it's not enough time. So we won't do unsafe, no vector API, no Graal, no bitmagic, no branchless code, no memory mapping, no Panama. Plain old good Java code. Okay, this is the baseline. Nice stream. The parallel is optional. We basically do the single threading version only because this keeps things simple. So we're going to split by the semicolon because it's a separator. Then we create a new measurement, which is a record, and it basically consumes the measurement, which is the split up string. And then we start to do this grouping using the grouping operator. we have the, I haven't seen the values, I have basically seen the values, and I'm going to join it, and the third version is the result, and this is then basically printing the string. So if you haven't played with the collector, aggregator collector thingy, give it a try. It's kind of slightly complicated at first look, but at the end of the day, it works nice. So we already know the baseline, and because everyone does AI, I kind of felt obligated to do this as well. So I asked Gemini for a solution, and because I have only the Hetzner machine still running, so I did this yesterday, it's 144 solutions. So if you ask Gemini, do this for me, the only thing you have to change is the formatter, you get 144. If you ask Claude, the first one is a fail with an out-of-memory exception. If you say, hey, it's going to be 1 million row, it then says, okay, let's try this, and you get to 122 seconds. Not too shabby, all right? And the solutions are kind of what you would expect. Good. Does anyone know what a flame graph is? So only a few hands. When you look at that, I will just make it a little bit bigger. It's a nice tool called Async Profiler, best open source profiler ever, probably the best profiler ever. You get one of the results in this format. And what it actually see here is your method calling other methods, and basically the wider this area is, the more time you spend. You can also hover over, and you see, for instance, here, it's a little small for the read line there. It's 17.7% of the entire runtime is spent in this section. And then of course, you can go into other details. You see, for instance, that the string split is about 32%. So it gives you nice insights. Good. So I gave you kind of some ideas. Entire runtime is 80% of the 100%, so 20% is overhead from the GDK, class loading, garbage collection, whatever. Then read line is 70%, split is 32. We have the parse of the double, and store and reduce, which is the mapping at the end. This is basically the runtime part. So if you do performance tuning, most expensive first, most bang for the buck. Let's do this. But you can't tune streams effectively, because it's a framework that's given, and you can only play within the framework. So let's unstream it for a moment and go classic. Classic means we have a nice loop, reading lines, doing a split, having two strings. The second one already gets converted to a double, and then we have a merge on a hash map with a temperature, which is kind of a holder class only. It's not a record, because I'm going to do nasty things later on, but it could be a record, and you can merge, and you always basically create initially an immutable object. So new measurement, joined, new measurement, joined, things like that. So this is basically the temperature thing, just to give you an idea. Everything is final, kind of could be a record, but for later tuning, it's kind of inconvenient. So ideas. How fast are we? And because we have two sites, just give me percent. How much faster is the unstreamed version? 5% faster. 20% faster. You're kind of very pessimistic. Or basically, you don't like streams. Okay, it's give or take 7 to 8% faster. And I'm not giving this away because we have way more of these coming up. Good. So is this surprising anyone? Is this surprising, or is this kind of expected? Yeah, I'm going with a single-threaded version only. So that's basically just ripping it out and saying, okay, let's do this differently. So in case you basically now say, hey, I can save 7% when I undo all my streams, don't. Don't run and do unstreaming, because this problem is 1 billion rows. If you read 10 rows, 15 rows, if you have a database in the back end, who cares? It's just, you don't have to. Clean Java code, that's what you have to do. But we don't want to do this here, right? So you can see things change slightly, so the percentages wobble around, but overall split is still the biggest problem, so let's take care of split now. So what can you do instead of split? Obviously in index off, we have just one separator. We get a position, we split the string manually, we do the other string, and then the rest is exactly the same. So, percentages, please. 2% faster? 10? 20, okay. 20. And if you have 2, just give it away. Okay, you might ask why. Because you might have looked into the GDK and you notice that the GDK says this. It's original GDK code. So what they do is if they find a single character instead of a regular expression, because split does regular expressions, they do all these checks and then basically say, okay, let's do the shortcut one and do just the character. But the thing is, as you can see, there's so much overhead to just check if we can do this trick. And then at the end of the day, we still creating a new array for the result. And by the way, intermittently, we create even an array list. So it's kind of a lot of code that runs. There's no better option right now in the GDK. For whatever reason, we should have a char-only version. So that's why this index of thing suddenly is way faster. If you want to really speed up your programs, and you think you have a problem with memory and garbage collection because you create all these intermediate objects, split to index of is one of the things where I say, hey, you can go. Just change this, because typically it's easy to test, shouldn't hurt that much. If you need regular expressions, different story, you can't. But if it's a single character thing, that's some nice winning at the end of the day. Okay, as you can see here, index of and substring is now together about 10%, so 16% faster. And the rest obviously is redistributing. So these you can't compare these numbers exactly, because obviously we have 80%, and then the share basically is redistributed of all the runtimes. Okay, so parse double would be the next one, which is kind of cheap to do. So I'm doing read line last. So this is cheap. Let's do less parsing. By the way, this is the original problem, and you don't have to read the code. This is double parsing in 224 lines in the GDK. Because double parsing can do all crazy shit, sorry. So it's plus, minus, different number formats, stuff like that. So it's really flexible. It can really do everything except predicting the next lottery ticket. So get rid of a lot of code would be the next step. I had, by accident, a version written before that's way simpler and basically does double parsing. By the way, if you do this on your own, you will see a lot of problems, because when you create a double, it's not precise. So if you have a lot of digits after the comma or after the separator, things can turn a little bit sour. So the GDK might claim a different double than what you create, but for our purpose with one digit at the end, that's an absolute okay solution. We just look at all the characters. If you find a point, we remember it. We do a character conversion, so minus 48, because it's ASCII. Then we have the number. We sum it up. And by the way, I said no bit shifting. This is basically times 10, just in bit shifts. A good compiler does it automatically. A good hotspot compiler does it automatically. And even a good CPU is just seeing, oh, times 10, let me do this in bit shifts. So you summarize this, sum this up, then you do the negative one if you have seen the minus, and then you're good to go, and you multiply it with position. Good. You know the drill? 5? 10? How much is this? 15, 16? So anyone was close? Okay. Nobody dies today. Might be injured, but nobody dies. Okay, good. And once again, the most important part here is that you see that your machine, the Intel machine, DigitalOcean Cloud, is picking up steam more quickly than the Hetzner version on an AMD CPU. So your tuning, and this is one of the things I will wave the entire time, depends on the hardware you're running on. So if you basically tune on your M3, M4, and you basically say, hey, it doesn't get any faster, it might, because you're running your cloud on a different hardware stack, or vice versa. You might tune it very much on your M3 because it has huge caches, and then at the end of the day you end up here and you don't see an effect, or the opposite. That might happen too. Good. So parse double minus 10% for the overshare, merge and read line are still big. Okay. So as we have seen before, it's basically this original line. We always created ourselves a copy of a string, the temperature string. But if we, basically what we do is we just basically scan a string. So why not continue scanning on a string we already have, which is the original string we got. So we just continue scanning. We don't create our own copy, only for the city. And then we do this. So we save one intermediate string creation, and we get to some more nice runtimes. Estimates? And no price today? 5. Okay, 5 was good. It's a little bit more than 5. So just by saving this intermediate operation, you save a lot. And later on, we will see why. Okay. The new version basically says substring kind of cut in half, give or take. So this is cool. Merge and read line are still the problem. And here's one of the, once again, I have to do the AI stuff for some reason, even so I don't want to. Double is what nobody wants to do nowadays anymore. Because double, first of all, in your daily work, double is absolutely fine. You are not going to run in any performance problems with your standard work in double. If you do a ton of calculations, if you do AI models, you are not going to do double anymore. You basically want to go int. And AI models even want to go short int, kind of 3 bits, 4 bits instead. And there are new data formats for it. And there's even an AI proof of concept that you can do 1-bit AI models. It's just basically kind of probabilities. And the 1-bit model was so good that it just achieved 80% of the other models. So you can go with 1-bit calculations for probabilities at the end of the day. It doesn't make any sense in my mind, but it just works. This is how AI works. So we do this here and just replace our double by integer. Why? Because we know the number format. We only have 1 digit, so we can drop this decimal separator and just postpone the entire operation to the end. After 1 million rows, we will do once the conversion and shift the digit by 1. So almost the same code, besides that I'm not remembering the position of the dot, I'm just skipping. Okay. So, ideas? Because this is such a nice question, we get more of these. 20%, okay. 5? 15? 10? It's not that much anymore. If we would have had this conversation 10 years ago, or maybe in the beginning, let's say first JFocus, and I would have done this, this would be huge, because processors at this point in time were kind of really bad with doubles. Nowadays, it's not that much anymore. So, but it's still good. You save because a double is 64-bit, an int is 32-bit, and you can run with a shorter format. Okay, fine. So we squeeze the lemon a little bit. That's not enough. We want to do 20%. So if you remember the original code, we have this lambda in it where we say, hey, in the hash map, if you add this to the hash map, if you already see it, run this lambda and merge it. Right? And because we know lambda is bad, probably. I don't know if you have ever heard this, but that's the saying. We do this and basically classify our code and say, let's go for the city, do a get on the hash map. If we find it, we just basically say merge the old and the new, which still creates a new temperature value. If you haven't, just put basically new temperature in. That's the idea. So, nothing. 3, 6. Why? Anyone? Gives you an extra bonus point. Yeah, so problem is we go into the map and say get, and the map then forgets the hash code operation. and then we do all our stuff, and then we do a put, and the put basically has to do all the hash code operations and reach into the map. So we do twice the work as we have done before. But I leave the code in for one apparent reason, because I want to tune it further, and you can't tune the original map. So, as you can see here, get operation 10, merge is 2, put is 5. Okay. What we do right now is always a new temperature model. And you say, basically giving presentation A1 right now, would say, keep your Java objects, because this is Java, you have to have objects, immutability is cool, records are great, stuff like that. If you want to do shit tuning, no, it's not. So we have to go immutable now to really speed up things a little bit. So instead of having an immutable temperature, we basically give temperature the ability to update itself with the next double, or the next int in this case, and if only we don't have seen it before, we will do a put operation. Not all the time, just in this case. So, 5 from 50 or from 53? From 53. 2. It's a lot. So it's basically from the original one, tuned further by 6%, give or take. You can see on the other side, it's a little bit more for the headster machine. This one is cool. So, yeah, if you do this, you can save a lot. Go mutable. Sure, functional programming, clean code, blah, blah, blah. Parallel programming, but, you know, speed. So, this is important. Good. Merge and put, gone, because we are mutable. We don't have to spend any time on that. This is basically where we spend all the money, and of course all the other percentages shifted. So I ripped out split because it's complex. I basically decided to go with my own double. The next logical step would be go with your own hash map, because it's an all-purpose hash map you have in the GDKs. It does everything. So this is the quick drawn how a hash map works. You have an entry. It's somewhere in a huge array. You calculate the hash code, the offset. You jump there. You get to an object. It holds key and value. You compare the key. You're cool. If you have a condition, you have basically a chain, simplified, a chain of objects you have to search through until you find the right key, or you don't. Here, in this case, Java has some nifty tricks going on. They build up a tree for the chaining. So if you really have bad hash codes, the operations are a little faster than searching a linked list. It's just really a tree operation which gives you left or right and makes things quicker. So, but obviously I'm a computer scientist. I claim I know how algorithms work. I basically say, hey, open hash map it is. So instead of going a complex way with all these additional objects and all the chaining, we do an open hash map. We store key and value in the original array next to each other. If we have a collision, we basically go one step further and just put it into the next slot if it's open. If not, I have to grow the map. Other than that, as long as I don't find any empty spaces, I'm still in this chain of collisions. We don't have this wrapper anymore, so this seems to be cool. And when you read the value, you basically already have it in your CPU cache, because the CPU always reads 64 bytes at the same time. So moves the entire array. 50 minutes, damn it. So we have to run a little quicker. So I found this on the internet, so basically use this, and it gives me a new implementation. And now you have to tell me how fast this is. 10%? 50? Okay, so once again, the original hash map is great. If you use it, don't rip it out, because you can't get to a better one. So it's really good all-purpose implementation. Nothing speaks against the original hash map. If you do still hash table, which I don't hope so, of course, switch it out, but otherwise, we're cool. So, as you have seen, what I now do is basically I say, okay, this is the original one, the open hash map, key and value. That's stupid. Let's merge this into key. And the key holds now also the temperature. So basically, we unify key and temperatures into one object, which gives me only one object I have to use at the end of the day. And so I call it an open set. And the beauty is now, when I go into this not longer all-purpose hash map, because it now can only do temperatures, I can make the decision between putting it or just updating it. So I don't have to do the hash code calculation twice, because already I have the right position and I can do all inline basically. Don't have to jump to other methods, stuff like that. That's 400. Nope. Okay. It's just a little bit of improvement. So it just gives us 2%, not that much. So we squeezed the lemon a little bit and said, okay, I/O is our problem. So let's sit back, enjoy some music, and think about it. At the end of the day, what we have is strings and doubles. When we really look at it, that's what we got in the original file, if we read the file just as file, not as information. So it's just bytes. It just condenses down to bytes. At least 6, no more than 107, right? So why don't we postpone string processing till the very end? So we are not reading a string. So this means we don't read characters. We don't do the Unicode conversion for all the cities again and again and again. We just basically say, oh, these are bytes, cool. Postpone this till we really output at the end of the day the city. So instead of doing 1 billion conversions, we do 413. Different algorithm, same result. And here we basically switch to a random access file instead of going with a buffered reader. You don't have to do this channel stuff. Later on I will have an example where you basically save on it. And the difference here is that I do a little bit of the handling of the file myself. So a byte reader is really cool. The byte reader basically does everything for you, but if you read only a byte all the time, so but give me the next byte, give me the next byte, you have a lot of overhead. And so instead of having this overhead, I basically say, okay, byte buffer, do your magic, and then give me your array, and I'm basically working on the raw array until it's basically completely read. And I basically say, okay, here's your array updated, and then I continue on the array. So I do primitive operations instead of object operations, which gives me a great advantage. On the right side, first I'm looking for the semicolon, just going over the array. When I found this, I remember it, and then we're going for the new line. I basically have all these positions, first, middle, last, and this is where then the parsing continues in the classical fashion. Have a key, have the doubles, all that stuff. So, give me the target number that will appear here. Okay, 23. Who was closest? Be honest. Close, right? So, good. As you can see here, it's a huge leap. And by the way, just for your say, in room A1, he said, René, you can't eliminate objects. I said, okay. Here's your version with objects. It isn't really that bad. But then I realized in this version, I changed 2 things at once, not just the objects, but something else. And I rewrote my original version, and that's basically now 28%. Because I found basically some more ways to optimize things I accidentally applied to Jose's version. Okay, so we're faster. We're not there yet, but we're close. So, you know, something happened. And this is something you get for free. So if you look at the original problem, when you run your program with 4 gigabytes of memory, you can also run this with 1 gig, but 4 gig gives a little bit more space to the GC. And you basically want to experiment how much you churn. You basically just pull out the epsilon GC, which is a non-garbage collector. By the way, what does a garbage collector do? 2 things. And? Not really. It's the memory allocator too. So it gives you memory and cleans up memory. So most people think it's cleaned up memory. No, it's not. It's giving you memory, and it's basically giving up the memory. So it's both things. So the epsilon GC gives you only memory. This is the part it can do, and the other one is just dropped silently. So here, because obviously we need a lot of memory, I limit this to the first 10 million lines. If you run this, you will see that you burn for the 10 million lines about 3.2 gigabytes of memory. If you multiply this by the total number of lines, you get to about 320 gigabytes of memory you would need without a garbage collector at the end of the day, that's basically your churn. The best solution so far, before we did this crazy stuff, was 104 gigabytes. And now you estimate what's currently going on. 20? We still have 20 gigs churn? Anyone? 10? Megabytes, not gigabytes, megabytes. So this final solution runs 1 million billion rows in less than 4 megabytes of heap size. You can actually restrict your heap to 4 megabytes. Did anyone do this before? Running a program with 4 megabytes of heap? Oh, one hand. Okay. So we are garbage collection less by accident. It wasn't by design, it's just basically by accident. So you can now stuff this into the smallest Docker container you can find and restrict this. It saves you a lot of money in the cloud if you have to pay for memory a lot. By the way, this is the SAFE solution where I had to promise to keep some objects alive. So it's basically 21 gigs. It's still okay-ish, but it's, you can save more. That's basically. So we exhausted cheapest tuning. I did basically a little bit more tuning on the integer one. So instead of having a loop, I basically have a program that runs from the top to the bottom instead of looping, because the CPU doesn't want to go back. It hates going back. And also the CPU hates branches. And if you go back, you have a branch. If you go back, you have a branch. So I basically have only a few branches that are basically relatively simple. So this solution gives you a little bit of extra oomph, which is about 1 to 2%. Cool, but still not where we want to do. So we have to change gear a little bit. But we still know that hash code and equals, if you look at the last data, is the problem. So we have to see if we can improve on that. First of all, you might just look at your code and find that. So by the way, math min and math max are intrinsics. So these are basically native code at the end of the day, so the GDK is really efficient. But if you run this code, you always update min and max. Doesn't matter what happens. So if it's bigger or not, whatever, you always update min and max. So this solution on the right, even so it's plain Java code again, basically does the following. Only if you have to update the value, and if you already updated one value, you don't have to update the other one. Doesn't make any sense. So we have min and max, and we save a little, keep this in mind. And then we have to look at our hash code calculation. So far we have the huge byte array, and we're running to find a semicolon, and then we do some more stuff and find a new line. And later on, we basically say, hey, hash map, do this for me. And the hash map says, okay, I need the hash code, and goes over the same data again. Why do we do that? So let's put together the initial search of the semicolon and the hash code calculation and keep the hash code instead. So instead of going twice over the data, we just do it once. And if we run that, we get to all these data points. And because I'm almost out of time, you can see that the min-max stuff brought us about, give or take, between 0.3, 0.4%. The early hash code, that's basically what we do right now, fixed the problem on the Intel machine, so I basically succeeded. I promised you 20%, here are 20%, but the Hetzner machine, the AMD one, I still lag behind. And because we are out of time, we have way more versions of this. And if you look into the GitHub repo, you will see this at the end of the day. I will succeed. And the red one, by the way, is the dangerous tuning, because if you have only 400 cities and you have an array that's huge enough, you never have a collision, so you can drop your equals operation silently, and you have a correct result until someone comes with 10K of cities. So this is just marked in red to see how much you would gain if you just drop equals. Kind of you drop 5–6% you would gain. And then I started to do other nasty things to my implementation. So for instance, I was unrolling a loop manually. So instead of doing one operation, jumping back, I'm basically doing two operations and jumping back, and the loop is then basically by steps of 2 instead of steps of 1. And this brought me to the solution that also fixes the AMD problem, that I still have to address the AMD one, and now we're here at 19%. And of course, I haven't given up. We still run normal Java code, and at the end of the day, we get to this final solution where I found an extra add I do, which was stupid. and then you squeeze the lemon completely on the last solution, and you get to 12.5% here and 17.3 there. That's the single thread version as fast as it gets. But there is no error handling in the code. It always assumes the data is correct. If the data is not correct, toast. So also all the original solutions of the 1BRC are all without error handling because we got promised an OK file. So we act like it is an OK file. String conversion can absolutely fail. We can fail double parsing. We could have a problem with the new lines, blah, blah, blah. So this is basically where we got to. 3 minutes left. So I can give you some more numbers, and of course I can give you the rating code. We replaced a lot of standard GDK functionality just to basically get from a generic solution to a very specialized one. That helped us a lot. We got rid of a lot of allocations. Basically got us to a non-garbage collector version by accident, wasn't designed. We have exploited all the boundaries of the input format. So no error handling, we know this is fixed, so we basically can read ahead because we know there will be one more character in the array and it's safe to just go there. We eliminated wrappers, we went immutable, and we try to utilize caching as much as possible. So the open hash map one is basically just playing with the caches. And then we did some, in the other solutions you haven't seen, branch removals, so because the CPU doesn't like to branch and stuff like that. Here is the raw data. The left one, and this is basically CPU statistics you can get from your CPU if you run this. You can see we spent about 540 cycles on the original baseline. A cycle is basically hertz. 540 cycles per line, so 1 billion lines, 540 billion cycles. If you read instructions, you can see one line takes about 2,300 instructions to process, and in total we run about 522 branches per line, which is a lot. The tuned one, this is one of the intermediate results, is down to less than 100 cycles per line, so factor 5. We are down by factor 7 on instructions per line, and we are down by factor 10 on the branches we are running. And this is where the biggest speed up comes from. Not just eliminating instructions, because the CPU has a lot of capacity for instructions, but branches is always something that's bad. 1 minute. And so the only thing that I couldn't eliminate is the branch misses entirely. And now we just look at the resolution that Thomas provided. That's basically my best solution so far, and this is his best solution, not Graal, right on the GDK right now. You can see that he cut the cycles by even more, so it's just 40 cycles per line. He cut the instructions in half, and this is the big thing, he further cut down the branches by factor 3, and here is the part that really makes the code fly. He has almost no branch misses. So when the CPU sees a branch, it's never missing the branch, so it's always predicting correctly. It goes into this area it has done before, so it's basically really running quickly. So it's basically really exploiting the possibilities of the CPU architecture as much as possible, and this makes the final code fly like hell. And this also makes it unmaintainable because you only do bit shifting to see things and manipulate things and convert stuff, and it blows my mind, kind of. So just a lot of data you can see for yourself at the end of the day. If you go cloud, you get different results for all the clouds, also for the tuning. You can get different results on GDKs. You get a very nervous cloud, for instance. If you run stuff, you can see if you measure on the same cloud machine, you get really different results. This is very important that you keep this in mind. And so we are at the end. The first 80% are not really that bad and that hard. So most of the things you have seen, you can take home. So don't rip out split everywhere. Don't rip out the hash map everywhere. There might be, a solution where you need to do this, but it's not a general purpose suggestion to do this. Tune one thing at a time, see how it pays off, and then go for the most expensive one in the beginning, and then you're good. So sorry for running at the end, and I have 4 more of these if you like. I have this bag, and I have a lot of pins and fridge magnets, so just come and grab some stuff. Thank you.
Thank you, René. I think we have very short of time now, but if you have questions to René, 1, 2 questions maybe very fast, I will send you this microphone. And I will also give you a gift card from J-Focus, which is for Rädda Barnen. Don't forget to rate this.
You pointed out that a split with just a character argument would be beneficial to have in the JDK.
Yep.
Are there any other recommendations like that where most use cases could be done better in the standard libraries?
Well, there are probably more. Let's see, the only one I directly remember. I think, for instance, the double conversion, you could have one where you give it the simple format and say it's simple. There's no different time format, different date format in it, or date number format in it. So it's known that this is not a faulty one. So it would be way faster. Split, for instance, it would be great to get a list back instead of an array. And the array basically comes back from a converted list, which is stupid. So you do 2 operations. You already have a list as a result. So it would be great to eliminate this. But you break the API, so you have to introduce a new one.
Thank you, René. And if you have more questions, I think you will find René here.
Yeah.
So pick him up and ask more questions.
One last one.